Okay. Hey, everyone. I'm Pratik. I'm a software engineer at Figma. Thanks a lot for attending this talk. I'm really excited to take Seattle systems forward. Today, I'll be talking about Protosockets. Protosocket is a message communication protocol that was built at Momento. It was actually one of my colleagues who's sitting here, Kenny, his pet project that he extracted out from his pet project and actually productionized it at Momento. Just a little bit of background about myself. I joined DynamoDB in 2018. That was my first gig after doing my master's at Penn State, Go Nittany. And DynamoDB, I worked on the control plane side of things, a little bit on autoscaling, IOPS and capacity management side of things as well. I worked for a couple of years at AWS Marketplace at the data platform team, re-architecting a batch processing system into event-driven system. But I sort of started craving being closer to the metal again than the application. I found a perfect opportunity at Momento for that, where I spent a couple of years working on the SDK team and the server team, doing a bunch of performance optimizations right from the SDK all the way down to the metal. This year, around 6 or 7 months back, I moved to Figma, where I'm working on AI infrastructure for our vibe coding Figma Make platform. For those of you who do not know about Momento, Momento is a caching and PubSub platform. I'm going to give a very high-level architecture of Momento before we talk about the actual protocol that was implemented. It's a very simple two-tier high-level architecture here. As a client, you have an SDK in various languages. You make a request. It goes via the AWS load balancer onto one of the routers. The AWS load balancer detects one of the healthy routers and redirects your request to one of them. The router unpacks the request. TLS termination happens inside the router, not at the load balancer because an NLB. Authentication, throttling, and all of that stuff happens on the router. It unpacks the request, sends it to the storage servers. The storage servers persist the request and sends a response all the way back to the client. There's a control plane, which is pretty much the brain of the system. The control plane sends any relevant metadata to the routers about where these storage servers reside, how many partitions there are, where should a client request go to. It provisions the storage servers, it does health check, and like all the state management stuff for the rest of the system. It was traditionally a gRPC-based architecture. So once you connect to one of the routers over TCP, it's an NLB. So it's basically a pass-through. NLB does not really care about what the application protocol is. It just sends the packets to the router. The router is the one that's doing the TLS termination, as I mentioned, and other stuff. And the router to storage communication was over unary gRPC, and the control plane communication to the router and storage servers are also over unary gRPC. So just a little bit of the background. This was the architecture circa 2024, June, July-ish, before we started making changes to it. Okay, so I have extracted, the other components. I just have the router and the storage here. That's what we're going to focus on for the next few minutes. As I said, the router communicates over using gRPC unary to the storage servers. Every unary request that you make is an RPC. An RPC request has some overhead associated with it. gRPC is basically a flavor over HTTP2. There's a network overhead. Every request has around 100 bytes of network overhead because of the data frames, the HTTP frames. And processing this request, processing every unary request, either on the router or the storage servers, incurs some computation cost. There are interceptors, there are other invariants that gRPC enforces, like the state machines, error handling. So both of these combined, the network overhead and the CPU cost incurred in processing the request, results in added latencies. So if you're a customer from your client SDK, it surfaces as more latencies. For a server team or for a platform team, it means less throughput from a single box. Horizontal scaling is cool. Throwing more servers at the problem always works. But the philosophy at Momento has always been trying to squeeze out the maximum you can do from one server. That doesn't mean increasing the number of cores or throwing more RAM at a single server, but it means given what you have, how much throughput can you extract from that single server?
How much traffic were you seeing? Like how many requests per second were each of these router machines handling?
Okay, now that's a good question. I had one of those slides for results later on, but yeah. No, that's fine. That's really a good question. I should mention that. So from a customer perspective, you can throw like millions of RPS at Momento, but every router before we did any of this re-architecture was doing 25,000 operations per second. The workload is 1:1 read-write ratio and less than 1 kilobyte items. So Momento uses RPC-perf heavily for benchmarking. RPC-perf is a benchmarking tool that was written at Twitter by the caching platform team at Twitter, and it's being used by a bunch of different companies, including Momento right now. So 25,000 operations per second for 1:1 read-write ratio, less than 1 kilobyte items was what these routers and servers together were doing before we changed any of that. Okay, so before re-architecting, the next step was, okay, what can we do? We need a servers to give more throughput. So what's the next step? So before we actually re-architected whole gRPC or any of the protocol, we moved to gRPC streaming, which is like a bidirectional stream. You get a bidirectional stream, and then you send all your HTTP requests or messages over that bidirectional stream. Just to take a step back, in the unary world, gRPC unary is over HTTP2. You don't need multiple connections for each request. They're multiplexed over one connection. With gRPC streaming, you get a further optimization where you can send multiple requests over a single HTTP stream. So with unary, you had multiplexed connections, but you still needed one unique stream for every request. That means opening the stream, processing it, closing it. With gRPC streaming, you can just reuse that stream to send multiple messages over it as well. So reusing the stream in addition to connection reuse, it's less header, less bytes. You still have those interceptors, but you still get reduced network usage and you still get reduced CPU cost. For us, that translated to 20 to 30% more throughput, which was good. I was personally happy. Kenny was not. Our founder Khwaja was not at that point. We wanted to do better. What can we do better? Before I go further, one of the downsides of any of these bidirectional streaming libraries or protocols, if you use, is it makes your implementation a little more complex. You get a lot of things for free when you're using an RPC model, a unary model, like error handling, passing in stuff you want on, passing metadata that you want through headers and whatnot. So the implementation does become a little complex. Okay, so before you can do anything better, you need to know what the problem is. And we were not totally sure what we were trying to optimize at this point once we moved to gRPC streaming. To know what we need to optimize, we need to run benchmarks. One of the benchmarks that really helped us here was flame graphs. So again, using the same RPC perf setup, the load test setup that we had, we ran flame graphs we generated flame graphs on both the routers and the storage servers. And we found a potential bottleneck on the H2 library. So before I go further, this is the stack you're dealing with in an asynchronous Rust ecosystem. So Momento, again, it uses asynchronous Rust. So you have this gRPC layer at the top that's using HTTP2. H2 is asynchronous Rust's HTTP2 library that's on top of TCP. It uses MIO. MIO is like a friendly abstraction over system calls that is provided by glibc. So glibc is basically, you can think of fsync or epoll and open and all the fun system calls that you get from any operating system. MIO is like a friendly wrapper on top of that. And on the bottommost layer, you have the hardware abstraction layer, which is the assembly code, and which provides you an interface to interact with the hardware. So after we ran our benchmarks and we generated a flame graph, there was one particular mutex or a lock that was observed in this H2 library. And every gRPC request that you send, and these things will vary across languages, so this is only applicable for the Rust ecosystem, but every gRPC request you send over H2, every request and response synchronizes on a single mutex within H2. What that means is like, now even if you have like multiple requests over the same stream, all these requests are going to block on that mutex, which is the input and output buffer inside the HTTP2 library. It was pretty hard to spot them. I don't know how Kenny did that. He had like a lens in his extra lens that he was able to spot a particular stack frame in the flame graph that's called lock contended. So if you ever see like bunch of log contended stack frames on your frame graph, it means there is a potential problem. Within Momento servers, what we noticed that each runtime thread parks itself for hundreds of microseconds and is not able to make progress when it hits this particular condition. So a router might have 6 to 8 runtime threads that's processing a bunch of different requests. Whenever it had to synchronize in this particular buffer, one of the threads made progress, but 5 of those or 6 of those threads potentially spent hundreds of microseconds waiting, just parked in the kernel, waiting to be woken up before it can process that request further. There's this issue still open. I think I actually Googled it this morning, and this is still open on S2 side. The title kind of gives it away. Library does not scale with multiple cores. So it basically means that if you keep increasing the number of cores or double the CPU, it's not going to help. That's the maximum you can do with the H2 library at least. Then comes Protosocket. Protosocket, as I said, was one of Kenny's pet projects that he pulled out from his pet project and threw it into the Momento ecosystem to see how it behaves. It's a message-oriented. It's not RPC-oriented. It's message-oriented. It's just over raw TCP. It doesn't have too many opinions. If you want ordering, you can use it in a way that enforces ordering. If you do not, then you can use it as is. It doesn't have any shared state connection. So what that means is like every connection you make now from your router to your storage servers, there is no shared synchronization between the connections, which was the case in H2, where even multiple threads and multiple connections were contending on a shared state or a shared buffer. In case of Protosockets, every connection gets its own input and output buffers. And even within those buffers, the synchronization points are quite minimal. I won't go into super nitty-gritty details, but if you look at it's an open source library. There's a bunch of cool stuff going on between swapping hash maps to keep these locking points as minimal as possible. Okay, so we spoke about this stack. Now, what do we get? So these are the two abstraction layers that we got rid of. Once we switched from gRPC to Protosockets between the router and the storage, we got rid of gRPC, we got rid of H2, the H2 layer. We're directly using TCP. We still use MIO because it gives you those friendly abstractions over ePOL. It's a readiness-driven library. It's like the philosophy of MIO is readiness-driven events. So you don't have to reinvent the wheel. You still use MIO and directly talks to the operating system. We use Prost. We still use protocol buffers. Prost is a library that in the Rust ecosystem that's used for protobuf for encoding and decoding messages. Protocol buffer was still a valid choice. It compacts your data. It packs your data more compactly as compared to JSON or even message pack, as a matter of fact. So we still went ahead with that. Okay, so I spoke a little about this before. Prior to any of this re-architecture, our routers or one router, one storage server with a replica combined was doing 25,000 operations per second with P39s less than 5 milliseconds. So that's kind of a benchmark which Momento tries to test against. It keeps changing. But with Protosocket, they were able to do 70,000 operations with P39s less than 5 milliseconds, which is almost like a 3x boost. So if you needed 100 servers for your workloads, now you need like 35, 40 servers for your workload, which directly impacts your company's revenue margins, not revenue, but margins at least. We also noticed that the degradation, like even if you're pushing your workload beyond 70,000 operations, the degradation in latencies was quite minimal compared to using Unity gRPC. So in Unity gRPC, at like 30,000, it went from like 5 to 40 milliseconds. But with Protosockets, if you went to 80,000, it goes from like 5 to 10 milliseconds. So the step-ups in the latencies as you increase load was also seen to be more graceful in case of Protosockets versus gRPC. This is actually pretty cool. This happened after I left, like 6 months back. I was like so impressed that the team did it, and I wanted to add this. Earlier, we were talking about just the communication between the router and the storage servers. One of the goals was to extend that to the SDK, which comes with its own set of challenges. Within your VPC, within your own ecosystem, within your own servers, you can do a lot of things, right? Like there's no authentication issues, there's no security concerns. But once you expose this to the client, you kind of open a different kind of worms. So the current architecture, from the first slide or the second slide to now, this is how the current architecture looks like. You have a client SDK in multiple languages. I think this is in a couple of languages implemented already. So the first thing you do is you talk to the control plane via the NLB. I'm missing an arrow here to discover all the routes, like all the routers. So the first thing the client does is it establishes a connection with Momento. It gets all the available routers, the IP addresses of all the routers. As a part of that first request, authentication also happens. Once it gets all the addresses in a round robin fashion, it sends the request to the routers over this long lived bidirectional Protosocket connection. As an additional mechanism, the first message that you send over this Protosocket connection is an authorization or authentication command. So the first step of authentication is when you get the addresses by talking to the control plane. And the second step of authentication plus authorization is the first message that you send as a part of this long-lived connection. If you try to send something else, the routers are going to reject that message back to you. Router to storage was happening over Protosocket, and the SDKs to routers are also now happening over Protosockets.
I think your question was NLB already does TCP load balancing. Why not just connect to your routers through NLB? And that does work. We've done that. But why not is because NLB charges you an extra 1 to 200 microseconds. And it also charges you dollars and cents for pushing data through it. So it's it's more expensive and it's slower. And so if you're optimizing for steady state requests to be as fast and as inexpensive as possible, it's nice to bypass NLB when you can. Also, if you're doing like a VPC peering relationship with a client, you can do VPC local routing and have basically free networking client to server, which is pretty cool. We've investigated a couple of different ways to peer. Usually we do the private link endpoints. But this new pattern was made in part to help ease the way that we would vend out like 10 dot IPs. This is very new stuff, like Pratik is saying, and this is unblocking us to be able to give nice VPC peered CIDR routes to some of our interesting customers.
So the question was, how does the client know if there's a deployment on the router or something went down and a new router came up? The SDK keeps refreshing that list of addresses from the control plane.
Would the router have DDoS authentication authorization, things like that? Yeah, Momento's router is a multi-protocol web-facing front end, so it does a lot more than just client SDK Protosocket stuff. It also has HTTP support. You can put like a URL into an IMG tag on your website, and it will load values out of your cache like directly into a DOM. So there's a lot of extra stuff that you can do here, and like fine-grained access control. Like a per key scoped tokens. That you might imagine are important. If you're giving someone access to to your cache through their smartphone's browser. We've also got like topics, which some of our customers use for like chat or for video game state propagation out to end users. So that router box, it's a lot more than just like an internal service detail. It's kind of a core to the way that users interact with Momento.
Of course, latencies. With NLB bypass, these are like some of the latencies gains that the team witnessed, like at P50, P99, P39s. It's pretty much double with NLB and without NLB. There's obviously a bunch of trade-offs when you're doing some of these things outside of your traditional infrastructure ecosystem. Proxies, firewalls, they all understand HTTP. We just can't get away with it. As I mentioned before, implementation is definitely more complex. There's a lot of things you get with HTTP for free. The question is, we can directly, why do we need the routers if we have Protosocket and just not publish the storage IP addresses at that point in time?
Yeah, you need to make clients fat, and then placement is at issue here. So the control plane does a lot of stuff behind the scenes. If you're trying to scale up, scale in, or do a deployment and change like your cache topology, there's a lot of coordination that you've got to do between the control plane and any of the clients. So inside of AWS, when you're sending your state, like the state of your storage updates to your routers, that happens very, very quickly. If you're doing it over a possibly public network to the client SDK, you may see elevated errors. Our customers reach out to us when we return them one error in a lot of cases. And so our deployments, have to depend on things like HTTP do go away. Traditionally in Protosocket, we've done some stuff there, but I expect that we'll hear from customers as they start using the Protosocket version that they don't like that they see a moment of errors on a deployment. They need a graceful failover. So yeah, basically to make sure that we don't give users errors, we don't publish those storage IPs directly. Also, they don't have authentication authorization built into them right now. It is a thing that we talk about though on a regular basis. Like, is this customer, or is this use case the right time to add our authentication and authorization to our storage nodes and publish them? It's something that comes up, and I wouldn't say that we're fully settled on the request flow that we have. But for now, the router is the thing that we talk to, at least over the public network. Yeah, that's 2 hops. This is, I think these were client-side latencies as well. I don't remember the test setup for this test. I'm pretty sure this was a client-side test. I didn't run these tests, but yeah, and I had it in the back of my head that it was about a 200 microsecond difference for NLB bypass. These are with, I think, larger nodes pushed at much higher throughputs. We've got 4x or 8XLs that we do 600,000 or 700,000 requests per second on now, which is quite hot. And I think that's what these tests came from. As for how many microseconds the router is charging you, that is in the low 100 to 150 microseconds territory when you're using a non-blocking RPC library like Protosocket. When you're using gRPC, it's much more variable due to the contention, the lock contention inside of the H2 library.
So if I understand the question correctly, you're saying, where does this performance improvement actually matter? In my personal experience, I've seen it matters when your tail latencies are impacted. So you probably wouldn't see it at P50, P90, P99, but you'll start seeing them at 4 nines or 5 nines. For product teams, usually I've also seen they make so especially if you have a microservice-based architecture, you don't know how many layers you're going down, and every millisecond that starts to add up pretty quickly. And that's just based on my experience in the past, where even a millisecond of tail latencies start mattering when there's a cascading failure situation, when you have a retry storm, in basically a SEV situation. In steady state, you're probably right. No one cares. But once any failure mode hits, it's like a metastable failure at that point. So I think at Momento, that's why I think folks are quite performance focused, because we are tail latency focused a lot.
So what's the focus of the tail latencies? From the user's perspective, sure. Like if you're loading from the phone, you're not going to expect to see loading an image in 300 microseconds. But if the server can't generate the response for you in less than 5 milliseconds, then the user certainly can't receive the response in less than 5 milliseconds, right? Like the performance of your server limits the best performance that a client could possibly see in theory. So Momento, yes, is available to users over public link, but Momento also has a lot of traffic that stays local to AWS and local even to availability zones. And in some deployments, they're AZ aligned. So it's kind of one of these things where if you're fast enough for your in AZ customers, you're going to be fast enough for your browsers. So I don't like it when people try to measure the latency to a smartphone when it's going over some public Wi-Fi at a coffee shop or whatever, and they're like, hey, why is this taking 60 milliseconds to load? It's like, well, take it up with Starbucks.
I just wanted to highlight a little bit of my personal experience with async Rust. I started on control plane on DynamoDB, which was not very systems programming heavy. We still use still JVM, a lot of fleet management challenges, not necessarily systems programming challenges. Spent some years again on the application side using a bunch of AWS tools or toys that I called to build a distributed system on top of it. And after that, I sort of moved to Momento, which was my systems experience. So I sort of moved top down. And if I were to go back 7 years, I would have moved bottom up, where I still don't care about this stack, the hardware level and what's happening inside the machine. But I would definitely start here. If you're new to system programming, which probably most of you are not, but still if you are, I would start bottom up. Open an OS book, write your own HTTP server, simple HTTP server, try to optimize it, make it event driven by using event epoll and other primitives, then go to the higher level abstractions and finally to the application. So just wanted to share my personal experience, because initially I had a very difficult time understanding any of this. Just acknowledgement to Kenny, you've heard from him already, and Khwaja just for sponsoring this and being a great champion, across the past 10 years. Yeah, that's it from me. Yeah.
So this is all written in Rust.
Yeah.
You guys have I just looked. You guys have a really impressive list of languages that you support. How are you integrating, out of curiosity, those the languages to the Rust implementation?
So it's gRPC. So before any of the Protosocket, so Protosocket is only in one of the client SDKs right now. But before Rust, I think we're implementing that in Golang using foreign FFIs. So I think the model there would be to use FFIs to integrate. But before that, it's all gRPC.
Okay, so all of those clients, with the exception of the Rust one, are all still using gRPC.
Yeah. Yeah.
Okay.
Yeah. Yeah. But as I said, this was built in the last 3 months, the client side layer. The server was built last year. Yes. The router, storage server, even the control plane is in Rust. It was in Kotlin, but even that's rewritten into Rust now. We were initially a Kotlin shop for the most part. Moving to a systems first language like Rust gave a lot of performance benefits on the server side, which is the routers and the storage servers we spoke about. And then just having control plane in another language, it just makes the onboarding for learning curve, and it's a mono repo, so the consistency of different things, it just makes it easier over time. And we had to rewrite a control plane anyway, so why not rewrite in Rust, which half the team already knows and half the system's already written in. So